So where things left off last time, we're talking about boiling water. Just to finish that story. So boiling of water is not a new phase transition. It's just the same phase transition that we call evaporation, where water is turning from liquid to gas. There's a net flow of water molecules from the liquid form to the gaseous form. In ordinary evaporation, that occurs only from the surface, the exposed surface of the water, so it's limited by surface area. But when you get boiling going, you have bubbles inside the water, and evaporation can occur not only at the top surface, but inside the liquid into the bubbles. So if suddenly you have a whole lot more surface area available, and the rate of evaporation skyrockets when you got those bubbles in there. The issue with that, okay, so why does that happen at a certain temperature? It's because you have to get the water hot enough that when there are bubbles of pure water vapor inside the water, they are dense enough by virtue of high temperature. They're dense enough to have atmospheric pressure, so they can stave off the surrounding pressure that would otherwise crush them out of existence. So at low temperatures, a steam bubble isn't stable. You could, in principle, have one there briefly, but it would quickly get crushed by the surrounding air pressure. Boiling temperature, they're stable for the first time. Any questions about boiling itself then? This assumes, when you talk about boiling, assumes that there are already bubbles. So if you've got a bubble, the water can evaporate into the bubble, produce high density steam in that bubble, dense enough to support atmospheric pressure, and the bubble can grow. But where did the bubble start from? And so the video that I was showing last time is the story of water that has been heated to boiling temperature or above, but doesn't have any bubbles in it. If you don't get the bubbles started, they won't grow because they're not there. The process of creating the first morsel of the new phase, the gaseous phase in this case, is called nucleation. And it is possible to be in a situation where you've got one phase present, in this case water, and by all rights, the other phase should be present and growing in quantity. However, you don't have any of that other phase present to start with. You have to nucleate it to get it started. Something has to kick it into shape. This happens in a variety of different contexts, and I'll try to remember to bring them back. But in this case, you've got water. It's hot enough to boil, but there are no steam bubbles. And how do you create this? The classic way to do this is in a glass or glazed container. Glazed means it's got glass coating, so your glazed ceramic mug actually has a coating of glass. Glass is a liquid that is frozen into a solid, but it's basically liquid-like surface. It's smooth right down to the atomic level. And as a result, it has no defects and little nooks and crannies to help create bubbles. And when you heat water in a microwave oven in a glazed or glass container, you can get it so that it's hotter than boiling, but it has no bubbles in it. And I got very good at doing this. This was like 15 years ago or something like that. That situation where you've got it hotter than boiling, and yet it's not boiling, is called superheated. So it's superheated water, and there's that video. I put the video that I was showing you. It's available on the Moodle site, the homework site. You can find the link for it. But it's got Chris Cuomo back in his early days chatting with me and responding to me saying, the water is then superheated. He goes, superheated? And, it's a big winner usually when I show it. So anyhow, superheated water. Normally when you heat water in a metal pot on the stovetop or a tea kettle or all those things, they have little bubble nurseries, little defects in the surfaces, little places where there's permanent gas trapped, for example. Permanent gas being like air. So a little air pocket trapped there. And that can keep spitting out new bubbles all day. And so you've got bubbles, places for the bubbles to form and grow. In a glass container, heat in the microwave oven, you can do it so there are no bubbles. And I got so good I got dangerous at making superheated water, and I've told a couple people, but there was a camera crew down from a Washington television station in our kitchen, and I was superheating a little container of water in our microwave oven, and I had it set up to cook for 30 seconds after it should have boiled, so it really hot, and they had their camera all set up, and we were all standing there watching it cook, and at 29 seconds or 28 and a half seconds into the cook, it boiled spontaneously. I was going to open it up and poke at it and make it start to boil. You introduce the first bubble and the whole thing goes bananas. It basically explodes. But it went by itself, and in that single frame, they had their camera set up with a real high frame rate and everything. In a single frame, it went from there's the water sitting there doing nothing to where'd the door on the microwave go, and where did the contents of the container go, and me going, ow, because the door hit me in the head as it flew open. So they aired that, but it wasn't quite the same. Okay, so public service announcement part of this then is, when you heat water in a microwave oven, be a little careful of it as you take it out, particularly if you've really just blasted it away and you open it, you realize it's just not boiling. It's just sitting there. It is possible to make it hotter than boiling without bubbles, and then it's dangerous. You've all seen a little bit of this. If you've heated water for coffee or tea or something like that in the microwave oven, and you've taken it out and you've put something in, like a tea bag, or sprinkled some sugar or something, or powdered milk or something, and it goes amusingly and sort of spits some water out. Surely some of you have noticed that kind of effect. That is slightly superheated. It's just mildly above the boiling temperature, and when you bring a little bit of gas into it, now it goes. A related phenomena is in all the carbonated beverages you've ever had, and champagne being sort of the classic. If you look at a champagne flute where the bubbles are going up, you look at it and you'll notice the bubbles are all coming from the same place in long streams. They originate somewhere. Basically, once you've released the pressure on those carbonated beverages, they're not superheated, but they're supersaturated. Same physics is similar. Supersaturated with carbon dioxide. It wants to come out of solution, and it can only come out of the top or into any bubble that's already there. So it comes out of solution and grows as a gas. So if you put bubbles in there, if there are no bubbles, it's going to have a tough time coming out as bubbles because there are no bubbles to grow into. So what happens is you have some little defects or dirty spots or little trapped air in the glass that act as the bubble nurseries to nucleate these bubbles. And once the bubble forms, then the carbon dioxide can go in and grow and make the bubble bigger and bigger. But next time you're drinking something that's carbonated, it being the weekend, you can do it tonight probably. Watch the bubbles typically come from the same place over and over and over again. And if there were none of those little bubble nurseries present, it wouldn't bubble at all. Anything else to say with that? Oh, and you might have wondered why it is when you shake a bottle of soda, it's dangerous to open it immediately thereafter. It's because when you shake it, you're putting lots of little tiny bubbles into the water, into the beverage. And the littlest ones you can barely see them, or maybe not even see them. They're the slowest ones to work their way back up to the top because of viscous drag forces. They're trying to get up, and they finally get to the top. You have to wait for them to get out, because if you don't, when you open it, there are already bubbles in there, and all carbon dioxide now evaporates into those, effectively evaporates into those bubbles, and they grow like crazy. So the whole thing, it's Mentos, same thing, you're making bubbles. Okay? Any questions about carbonated beverages and boiling water and not boiling water and superheated water? All right. One last thing to show you with water fun and games. So I've talked about the phase transition from liquid to gas, gas to liquid. So I can show you one cute thing to do with that phase transition. And let me get it started while I can talk while it cooks. What's happening? What I'm doing is I've got these are open cans of soda cans with a little bit of water in them. And we're heating the water now, hotter and hotter. And as it gets hotter, the phase equilibrium between liquid water and the gas water is struck at a balance between liquid water and gaseous water. The gaseous water has to be denser and denser for it to be in equilibrium. And actually, Al must have preheated this guy. So it's already boiling. So right now, the water is, the phase equilibrium, it's hot enough that the equilibrium between liquid and gas involves very dense gas, so dense that it's actually at atmospheric pressure. So this can is essentially completely filled with water, nothing else. It's water vapor, however, and if I drop the temperature abruptly, that water will turn, the vapor will turn back into water, and there will be essentially nothing in the can. And the result is the can suddenly becomes virtually empty except for a little bit of liquid water around. And even though I don't seal the can, can you follow the idea of what just happened? I can talk it to death or not. I'll get it hot again. This guy, I'm boiling water in it. It's chasing all the air molecules out, the permanent gas molecules that are oxygen and nitrogen molecules. They're leaving, being displaced by water molecules, which are perfectly happy to be a gas in this hot container. But as soon as I put the container in a cold environment, those water vapor molecules, they're not happy to be vapor anymore. The landing-leaving effect is it suddenly becomes in favor of landing. So they all stick to the sides, become liquid, they condense, and what's left? A very dilute vapor of water or steam. So the steam goes from being atmospheric pressure to 1/100th of atmospheric pressure. The missing water molecules have become liquid. And suddenly the can has way too little inside to balance the crushing pressure of atmosphere outside, and the can goes whoomp. Ready? All right. One more? Yeah. This sort of demonstration has been done in this room a whole lot of times with bigger and bigger cans. So some of them, they do these pony keg ones. And then eventually, there was one that they did a 55-gallon drum like this. Heat the whole drum up, boil water in it, seal the drum, and just go on with the story. And it took like 15 minutes before it spontaneously cooled far enough that the pressure went low and it crushed. And it was like a sitting bomb there waiting for people. It was very, everybody was, yeah. All right, last one. Not very exciting. All right, you get the idea. Any questions about that? Why that worked? All right. Okay. That brings us to last bits of water, steam, and ice. I've talked about solid ice and liquid water, the back and forth, the freezing and melting, familiar. I've talked about liquid water and gaseous water. That's evaporation when the liquid goes away and becomes gas, and condensation when the gas goes away and becomes liquid. You okay with those four phase transitions in concept? The last pair to bring up is the pair that involves solid ice and gaseous water and just skips liquid. And it's there. Ice and gas can exchange molecules, and they do. And when the ice loses molecules directly into the gas, which it does when the gas is very dry, meaning that there's almost no water vapor in it. The ice loses water molecules into the gas, and the gas, because it has so few water molecules in it, can't replace them. So the ice shrinks, the gas accumulates more water molecules. That's called sublimation. It's familiar, probably the most familiar version of it is dry ice, so-called dry ice, which is solid carbon dioxide. And when you have a chunk of dry ice there sitting on the table, you never see any liquid carbon dioxide. It's hard to get liquid to be stable at atmospheric pressure. So that dry ice simply loses molecules directly to the gas, and the ice just gets smaller and smaller and smaller until it's gone. Is it familiar? You've all seen dry ice somewhere or other? I hope. It happens with ordinary ice as well, and where you see this is in a frost-free freezer. I talked about this the other day. a frost-free freezer or refrigerator, your dorm freezers, they just have a cold surface in them that freezes whatever you put in the little window, the little freezer unit. And every time you open and close the door, water molecules from the air around the freezer encounter that cold surface, and they stick to it more often than they leave, and they accumulate on that surface. That's the other possibility here between gas and solid. It's the deposition. It's the reverse of sublimation. Water molecules sticking on a surface and accumulating there as ice. That's what creates frost. I'm in the middle of a story, but I'll tell you this, the last of the phase transitions anyways. So as water molecules just accumulate on a very cold surface, they just develop ice directly right out of the vapor, and that's called deposition. I don't care whether you remember the names. It's around. You've seen it as frost on the grass, for example, on a cold day, or on the windows on a cold day. It also forms in your freezers, the dorm freezers, because there's a lot of water molecules around, and given an opportunity to stick to that really cold surface of the freezing compartment in your refrigerator, they will accumulate, and they will become obnoxious sometime sort of mid-semester or whatever, and you or your roommate will have to decide who gets to defrost the freezer and get rid of those big chunks of ice. But that ice came right out of the air. So far, so good? Or questions about that? Frost-free freezers fix the deposition problem. How do you make it so that the ice doesn't accumulate on all the coldest surfaces in the freezer? The way you do that is by having an even colder surface somewhere hidden out of view that accumulates all the water molecules and actually makes the air inside the freezer so devoid of water molecules that even in the landing leaving process, even in the cold environment, there are more water molecules than leaving the ice surfaces than landing, because the air is so dry, there's so little moisture in it, that even though it's rare that a water molecule will manage to break free from the ice, it happens occasionally, and it's not replaced, because there's just no water molecules in the gas to land, or, so few. Is that okay? So a frost-free freezer accumulates all the water that's in the vapor in back where you can't see it. And they occasionally get rid of that ice. They're accumulating it as ice. They get rid of it typically into a pan underneath the freezer. They manage to turn it back into water with heat, and they evaporate it into the room. So you should never notice it unless your freezer has some failure inside or something gets plugged. Then you might have an overflow of water from under the refrigerator freezer. But basically the idea is that it's super dry in the freezing compartment. No moisture in the air. The consequences of that, the good ones are there's no ice forming on stuff. The bad consequences are any exposed surface that has moisture in it will lose water molecules, even though it's frozen. So that's the origin of freezer burn. So this is public service announcement stuff. Like, you probably will all experience freezer burn stuff. Certainly the ice cubes themselves gradually disappear from the freezing compartment. Where did they go? They sublimed off the ice and got sucked into this catch-all for water vapor in the back of the freezer. So the ice cubes shrink away to nothing, and everything else is not wrapped up properly will get freezer burn, will gradually lose its moisture. It's getting freeze-dried. You may have heard of freeze-dried stuff. You can freeze it, and if you put it in a very moisture-free environment, even though it's frozen, it will lose its water molecules gradually until there are none left. So they make freeze-dried food, sort of astronaut-type food. Weighs nothing, has all the nutrients, I suppose, has none of the taste. You okay with that? So next time you pull out the little midget ice cubes out of the frost-free freezer, you'll know where the missing water went. All right. I got one last thing to say about water, steam, and ice. That's relative humidity. Another term you've heard your whole life. What's this mysterious thing? Today the air is humid. yesterday the air was dry. What's going on here? Yeah. The screen? Thanks. Hi, I'm still here. Okay. Never remember. Okay, so relative humidity measures the amount of water vapor in the air relative to the equilibrium. So at 100% relative humidity, when you're at the full humidity, that's when liquid water and the water in the air would be in phase equilibrium. The liquid water wouldn't be getting larger or smaller. The gaseous water wouldn't be changing. There'd be no net movement of water molecules between the liquid and the air. That's 100% relative humidity. So humidities typically are less than 100%. If they go, I'll say later what go above 100. If they're below 100%, that means that there's not quite enough water vapor in the air to replace water molecules that leave liquid. So the liquid might lose a certain number of water molecules, and the air replaces only a fraction of them. It's probably correct to say that if it's 50% relative humidity, that the replacement is only half as fast as the leaving. So for every 10 molecules that come off the liquid, only 5 return. And it's only 5 because the relative humidity is 50%. There's only 50% enough water molecules to match the leaving rate. So what's the import of relative, I should say also, relative humidity depends on the temperature. If you take the exact same air and the exact same liquid water and you raise the temperature 20 degrees, suddenly the air doesn't have enough water to match. The air's relative humidity suddenly goes down. Why? Because at that increased temperature, the equilibrium would be struck with a much denser water vapor in the air. It's hotter, it's easier for water molecules to leave the liquid water, so to match the leaving rate, you have to have more landing. You have to have a denser gas of water to match it. And if you just poured it over the same water vapor that you had at a lower temperature, and it was 50% relative humidity at the lower temperature, it's not going to be 50% relative humidity at the higher temperature, because that water, the density of water vapor is not nearly as close to the balance as it was at the lower temperature. I'm now rambling. I'll stop. So for any given temperature, what's life like with respect to different relative humidities? If you're at 100% relative humidity at this current room temperature, that means that if you put water out on a table, the water will just sit there. There will be an exchange of molecules between the liquid water and the gaseous water, but there will be no net movement. As a result, there's no evaporation. There's also no condensation. Evaporation would be if the liquid water shrunk. Condensation would be if the liquid water grew, and you get neither. So at 100% relative humidity, nothing happens. What are the consequences of that? Well, suppose you're all hot and sweaty, and you walk into the room at 100% relative humidity. You can't evaporate water molecules. Your perspiration's all over you, but it just sits there because for every molecule that leaves your perspiration, another one lands. It does you no good. So that's why when it is really humid, it's so muggy, it's really humid, you can't evaporate water well. And particularly, you can't evaporate perspiration. So it feels lousy. You count on being able to evaporate perspiration to control your own body temperature. Is that okay? High humidity, what are the consequences? It shuts down evaporation. When it's a dry day, 20% relative humidity. What that means is there's only 20% enough water vapor density to replace water molecules leaving a liquid. The liquid then it loses water molecules like crazy. There's a net flow out of the liquid into the gas. And with that flow of water molecules, there's also a flow of energy, because breaking free every water molecule from the liquid water takes energy. So the water, first of all, it evaporates like crazy because it's not being replaced. It's not fighting much of a return. And every time a water molecule breaks free, it consumes energy from its neighborhood. So it sucks up thermal energy from everything around it. And it will cool you off. If that's perspiration on your skin in this dry air, it will cool you off because you're losing water molecules, and with it, you're losing thermal energy. The thermal energy goes off and becomes chemical potential in those water molecules, but your experience is that you lose thermal energy and you get colder. Okay? It is the case that if you put a pool of water in the middle of a dry room where everything is at a certain temperature, let's say 20 Celsius, just to pick one and stick with it, the water in the dry air, the water will begin to evaporate. And as it does, it will soak up extra energy, thermal energy from the rest of the water. The water will cool. It will actually go below 20 degrees Celsius. And it will go colder and colder as it loses water molecules. So it really will, it will be out of thermal equilibrium. It will be cold, the coldest thing in the room. It will get colder and colder until it gets cold enough. Remember, as it gets colder, it has more and more trouble losing water molecules. Eventually, the rate at which water molecules leave will slow down enough that the landing rate will balance it. And at that point, it'll stop evaporating. So it will cool itself down until evaporation stops. And that temperature at which it cools down to the point where evaporation stops has a name. It's called the dew point. It's the temperature at which landing and leaving come into balance. And you could begin to condense water instead of evaporate it at that low temperature. And that's how dew happens. Dew is condensation on the plants and animals and whatever. So in dry air, a pool of liquid water will actually cool itself down significantly, a number of degrees. In moist air, it will not cool itself very well because it very quickly stops evaporating because it's dealing with so much return in the moist air. So one of the ways they measure relative humidity is by comparing the temperature of a dry thermometer with the temperature of a wet thermometer. The wet thermometer is self-cooling by virtue of this evaporation process. And the drier the air is, the more it cools itself by evaporation. So the bigger the temperature difference is between the dry bulb and the wet bulb. Okay? Little mysteries of life that you may or may not have done. I remember going off at a 5th grade camp thing in school and having a wet and dry bulb thing you swung around, and you'd read the temperatures there, 2 different temperatures. And somehow magically that told you what the humidity was. Well, this is why. This is how it works. All right? Relative humidity. So hopefully it'll mean something to you next time you hear people talk about the relative humidity and why you care whether it's humid or not humid. Okay. I think that's all I have to say about water, steam, and ice. So let me go on to clothing, insulation, and climate. The stories here are really controlling the flow of heat. How does it distinguish from the wood stove? We watched how heat flows from hot things to cold things. Water, steam, and ice, we looked at phase transitions and a few other aspects of moving heat around. And this now we're trying to, if you try to be strategic about making sure heat goes where you want it and not where you don't want it, these are the topics that are relevant. So if you want to stay as cool as possible while you're fighting a forest fire, what color clothes should you wear? So this is, if you're trying to make sure that you don't get heat transfer to you, you're trying to keep that heat away. You get choices: white, shiny black, flat black, or silvery metallic. You okay with the question? And these are what you see when you look with your eyes. So how many think that your best choice would be white? How many think your best choice would be shiny black, like glossy black? How about flat black? How about shiny silvery metallic? Yeah, silvery metallic's going to be the winner. The shiny black and flat black both have the problem that they are excellent at absorbing thermal radiation and emitting thermal radiation. However, your situation is that you're colder than the stuff you want to be saved from, so you don't want to receive its thermal radiation. Being able to radiate away your own would be kind of nice, But if there's any exchange between you and the fire, you're going to receive heat from it. Yeah, you can radiate a little heat toward it, but it'll radiate a whole lot more towards you than you do towards it. You're going to receive heat in that exchange. Is that okay? White is the weird one. White, as I've told you before, white looks white to our eyes, but it's real iffy in the infrared, or worse than iffy. In all likelihood, your white clothing won't be white in the infrared. It will be black in the infrared. So there are various cultures in which people wear black robes, and there are others that wear white robes and so on. In sunlight, there's a difference because sunlight is visible light. It's thermal radiation in the visible. It's high temperature thermal radiation, and the white robes will certainly reflect most of that. But in the infrared, they're both probably pretty dark, and they absorb a lot of infrared light. So silvery metallic is the best choice, and in reality, the forest firefighters, big deal this summer in California. They travel with emergency kits. I mean, the classic emergency kit is a little aluminum tent, and if all goes bad and they're about to have the fire burn over them, they want to get no conduction, convection, radiation. How do you do that? You clear all burnable stuff from a certain patch of dirt. You put the tent on the dirt as low as possible because convection takes heat up. Natural convection takes heat up. You want to be the lowest thing in the whole story. So you want to be down low. You don't want to be touching anything. So you don't even touch the tent walls. You try to stay away from anything, no conduction. And lastly, radiation. The aluminum goes on the outside, man. Reflect all the fire's thermal radiation back at the fire. And people survive the fires in those little tents. It's no fun, and it's probably not 100% effective, but it's better than nothing else. Okay? So some observations about clothing insulation and climate. Clothes keep you warm in cold places. They're fighting the exchange of heat from hot to cold, the transfer of heat from hot to cold. They keep you cool in very hot places. They go both directions. It works. Insulation in general controls heat flow from various objects. So you encounter insulation in 1,000 forms. One of them are the foam cups and whatever. Some insulation is more subtle, like I talked a little bit about modern windows, modern multi-pane windows. If you ever lived in a house that had only single-pane windows during the winter in particular, you know that it's a huge heat flow. There's a huge heat flow through that single-pane glass, and it's people, I guess, for some reason, people didn't worry about this 50 or 100 years ago, and now it's presumably the cost of actually trying to heat your house when you only got single-pane windows is horrible. And where I'll end up with the story is in the insulating effect, in a sense, of what are called greenhouse gases. That the more we put of these greenhouse gases, one of which is carbon dioxide, into our atmosphere, the more difficulty the Earth has in exchanging heat with the surrounding space, with the vast void of space. The story really is the Earth is receiving heat, just a synopsis, is receiving heat as thermal radiation from the sun. And it has to get rid of that thermal radiation at the same rate it comes in, because if it didn't get rid of heat as fast as heat came in, its temperature would gradually increase. So the Earth has long ago increased in temperature to the point where it manages to send heat off into the vast voids of space as fast as the sun sends it to the Earth. It's in balance. But the temperature down here at the surface of the Earth depends on how that balance is struck exactly. And so as we put more of these heat-trapping gases into the atmosphere, we'll stay in balance. The heat coming in and the heat going out will still match, but the temperature of the Earth's surface will continue to increase, which is not a good thing. Yeah, unless you really, I shouldn't say make blanket statements. Most people would prefer it not to happen. Okay? So the questions to go through, how does clothing control the three mechanisms for heat exchange, conduction, convection, radiation, and finally, why do greenhouse gases warm the Earth's surface? Okay, so first one regarding conduction, the flow of heat by conduction. If you're trying to limit how fast heat goes from one place to another by conduction, you've got a couple things to work with. And so I've got an equation up here, which really we only need to follow in concept. I don't care whether you ever remember this. The flow of heat from one place to the next depends on a couple of things that hopefully are fairly obvious. The first is the choice of the material, what's called the conductivity. Different materials have a different values of an intrinsic characteristic of the material. It's thermal conductivity. Copper has a large thermal conductivity. Stone or glass or plastic have small thermal conductivities. And you can go and look up for any material you like. You can look it up, just Google it. You'll find the thermal conductivity of these various materials. And not surprisingly, the metals tend to be on the high end, dramatically higher than most of the electrical insulators. And that's because the main source of conductivity in a metal is its mobile electrons. The same ones that carry electricity carry heat. So the conductivity of the material matters. Another thing that matters is the temperature difference between where the heat starts and where it ends up. The bigger that temperature difference is, the more heat flows. And it's pretty linear in the difference. So that if you double the temperature difference between inside and outside, you double the heat flow. This, for example, in the walls of your house, make it a stone castle so we don't have to worry about any complexity in the walls. You're in a stone castle and you want it to be 20 Celsius inside, which is sort of room temperature, and it's 0 Celsius outside, a certain amount of heat will flow. If you go to minus 20 Celsius outside, that's twice as big a temperature difference, you'll get about twice as much heat flowing out of your castle and you'll get seriously colder. Okay, so the temperature difference matters. The bigger the temperature difference, the worse things get. This, for example, explains why in the hottest of days, it becomes very hard for you to cool your house. The temperature difference between inside and outside is getting bigger and bigger. The heat, therefore, is flowing into your house, some of it by conduction, faster and faster. Bigger temperature difference. Okay? The other issues are geometry issues. The area through which the heat can flow, the more area you've got, the more heat flows. That should make pretty good sense. If you double the size of a wall, you're going to get twice as much heat through it. On the other hand, thickness appears as in the reciprocal of thickness. That is, the closer you bring the hot and the cold to one another, the faster heat flows. The steeper the temperature gradient becomes between the hot side and the cold side, and the more the heat just gets pushed through. So this explains, for example, why in housing insulation, you try to minimize exposed area because heat's going to flow, whether you want to try to keep the heat out or in, doesn't matter. The more area you expose to the other temperature, the more heat's going to flow. So keep it small. In principle, houses should be made round spheres because they have a minimum surface area. But I guess maybe yurts are like that. And you want to make it thick. So that's why a lot of walls, the thicker you make that wall, the farther apart are the hot side and the cold side, and therefore the less heat flows through it. So thick walls have become useful. We're okay with conduction? It's not a big story. All right, well, suppose you have two wool sweaters, and they're both 1 centimeter thick, but one weighs 50% more than the other. So they look identical, except one's got 50% more weight in it. Which of the sweaters will be better insulation? Will keep the heat flow, minimize the heat flow? How many think the heavier sweater is the better insulator? How many think the lighter sweater is the better insulator? Voting is minimal. Other quips come to mind, but I'll leave them. Anyhow, it is the lighter sweater that's a better insulator. Like why? it turns out the main insulation in a sweater and in most of our clothing, in our hair, in a lot of the building materials we use is air. It's not the wool in the sweater. Wool itself is not a good, it's an insulator, it's not a very good conductor of heat, but it's a lot better at conducting heat than air is. So if you had a block of wood, block of wool, and you put a hot side and cold side, heat would flow through it. It's kind of like a plastic, basically. It would be a bit like a big block of plastic, and heat would go through it. You can do better, and the way you do better is using air. Air is a terrible conductor of heat. If you can keep the air in place, don't let it move, and you put a hot side and cold side, you can have a very big gradient in temperature across it, and the air just barely gets barely notices and barely carries the heat through. So air, it turns out, is a very good insulator, but you have to keep it from moving. And that's what the sweater does. The wool of the sweater isn't there as the insulator. It's there to trap the air, and the air is the insulator. The wool traps the air by viscous forces. We've seen these before. You try to move air across a surface or a surface across air, particularly little fine details. The air rubs. It experiences forces due to viscosity, and it has trouble moving. And so the wool itself, the wool's job is to keep the air from convecting. Convection can carry heat fairly effectively. So you want to keep the air in place, and that's what it does. That's what all your clothing is doing. You're basically being insulated by air. So far, so good? That explains a lot of other kinds of insulation. A down coat. If you've ever gone shopping for high-end down coats or something like that, or bedding, they'll sell you down. Real down is it's feathers, and they will. You pay a premium for the fluffiest, loftiest feathers you can get. So they'll show you. I don't know, an ounce of El Cheapo brand down occupies this much space, and an ounce of super high grade down occupies this much space. It's fluffier, so you have less down, keeping the air under control in a bigger volume. So what you want in principle is the fluffiest down that you can get that doesn't allow the air to move. So eventually, if you get it too fluffy, I suppose it's so tenuous that the air can begin to move again. But you don't get to that extreme. So the lightest, fluffiest stuff is actually the best insulator. Where this shows up in your house, most of the insulation that's used in modern houses is air, and it's held in place not by wool. I mean, you could do it, but I should say it's tapestries. You know, you have a castle. A castle is made out of rock and stone and stuff. Is there any difference? I don't know. Those are not good conductors of heat, but they're not terrible. And so castles were notoriously cold. So what do? Trap air on the surface of the castle wall. How? With tapestries. So they were insulation. You know, way back when, for people who could afford them. I guess if you can afford a castle, you can afford tapestries. This is more modern insulation, fiberglass. So it's glass wool. It's just tiny fibers of glass. Amazingly, just as you can spin cotton candy, which are fibers of sugar, you can spin glass, make fibers of glass. And you can mat it together. And so this is how much does that weigh? That's 8 ounces or something like that. But it occupies a lot of space. Most of what's there is just air. And glass doesn't burn, so it's pretty safe material. There have always been issues about whether breathing it is it damaging to health. But in any case, it's mostly air insulation, and getting heat from one side to the other, well, what do you got? First off, conduction is terrible because the glass fibers are long and thin, and heat has to go from one end of the fiber to the other end of the fiber through this narrow little channel. They're not very good at conducting heat. And the air between them is terrible at conducting heat. And the air can't convect because it's held in place by viscous forces. So conduction and convection are both really having a terrible time carrying heat from, say, a hot side to a cold side. So far, okay? That leaves radiation, but with radiation, there's no direct line of sight from one side of the material to the other. So radiation from one surface might only go a few millimeters before it hits something. It gets absorbed, because this is all black in the infrared. And then it has to be re-emitted and then go another millimeter, be reabsorbed. It's very inefficient as well. So this stuff pretty much shuts down conduction, convection, and radiation. And the thicker you make it, the more distance there is across which the heat has to move, the better the insulation. So in houses, modern houses will often have something like this much. There are code issues associated with it. You might have this much in the walls. And in the ceilings, where the heat flow is particularly you can lose a lot of heat through the ceiling because convection is so efficient in the vertical direction. So they may have 12 inches or more, 18 inches of this kind of fluffy stuff in the ceilings, in your attics. So if you ever go look around your house for what's insulating it, presumably, assuming your house isn't more than 50 years old, it'll be a lot of this stuff. If your house is older, they put a lot of fiber in there. So this is cellulose fiber. It's kind of like putting cotton in your walls or in your roof, in your attic. It's got fire retardant in it. If those of you who walked in here wonder what was smelling, it was Al and me burning this stuff. I won't burn it because that's stinky. This stuff melts. Actually, what I will do, I didn't bring any pennies. These are fire bricks. This is really light and fluffy. This is a ceramic material with a lot of air in it. So it's very porous. So the main insulator in this is not the ceramic, it's the air. And so you can heat this thing seriously hot. What am I going to heat? Yeah. Things that I don't want to heat. Anyway, I'll heat it by itself. So can you see that it's getting red hot? If this were a chunk of metal, I would be in real trouble. But it's not. It's fire brick, and it's mostly air. The fact that it's a ceramic means I can get the ceramic incandescent hot without it melting. If I do the same thing with that cellulose stuff over there, it will start to smoke, which will be disgusting. And if I do it with the fiberglass, it will melt, which will be disgusting. But anyway, you get the point. Obviously, if I touch the spot that's glowing red hot, I'm going to hurt myself. But in my hands, no problem. Pretty good insulation. Okay? What does this leave us? So main insulation is air in houses. What I want to do next time, I'll tell you a bit about modern windows. I've said a few cents about that before, but I'll do it again. And then I want to make sure that you come away with some feeling for why putting various gases into the Earth's atmosphere will affect our climate, because that's, of all the topics, the most pressing and important.